Picture this scene. Deep in the vaults of the Royal Swedish Academy of Sciences lies a book treasured for 120 years, the Nobel Prize Registry. Within its pages, you can see the handwritten signatures of Einstein, Marie Curie, Feynman, and Niels Bohr, the scientific giants who changed our world. In 2024, a new name was added alongside these legendary figures. His name is Demis Hassabis, CEO of Google DeepMind. He won the Nobel Prize in Chemistry for cracking one of life science's greatest puzzles: how proteins fold into their complex three-dimensional structures. But what might surprise you was that this world-changing scientist originally dreamed of being a video game developer. From writing game code in his bedroom in the 1990s to using AI to redefine scientific discovery today, his journey shows us that the most humble beginnings can lead to the most extraordinary destinations. Let's rewind to the 1990s. Back then, Hassabis was obsessed with creating intelligent game characters. He recalls the painstaking process of hand-coding every polygon in physics engine, programming complex algorithms line by line to achieve realistic water reflections or natural material behavior. But a bigger vision was taking root in his mind. What if machines could learn these patterns themselves, instead of being explicitly programmed by humans? In 2016, that vision became reality. AlphaGo defeated World Go champion Lee Sedol. This wasn't just another computer victory, it was a watershed moment for artificial intelligence. During the match, AlphaGo played the now famous Move 37. The move was so unconventional, so outside the box, that professional players gasped. It completely defied thousands of years of human Go wisdom. Data showed the probability of a human player making that move was less than 1 in 10,000. Yet it ultimately proved to be brilliant. In that moment, people realized AI was no longer just mimicking humans, it was creating entirely new intelligence. This breakthrough sparked the fundamental question: if AI could demonstrate creativity in a game, what could it create in the real world? Recently, Hassabis provided a stunning answer with the Genie 3 model. It's an AI that can generate complete, interactive worlds from simple text descriptions. Let me describe just how mind-blowing this is. You tell the computer, "I want a volcanic landscape," and within seconds, a navigable 3D environment appears on your screen. You control the perspective with your keyboard, and as you explore, new terrain generates in real time. And when you turn around, the areas you've already visited remain exactly as you left them. The world has memory and continuity. Unlike traditional game engines that require programmers to create every 3D object and code every law of physics, Genie 3 operates differently. It learned by observing millions of videos, reverse engineering principles like gravity, light reflection, and material properties without explicit programming. This represents a fundamental shift in content creation. What once required teams years to build can now be generated by anyone with a single sentence. Of course, the technology is still in development, but there's a deeper significance here. These world models are helping AI understand physical reality, a crucial step towards artificial general intelligence. For AI to become truly general, it must understand not just abstract concepts, but also how objects move, interact, and behave in three-dimensional space. Since AI can already create worlds, how close are we to superintelligence? Hassabis's view is remarkably sober. He argues that today's AI systems have PhD-level intelligence is nonsense, because even the most advanced chatbots can still make mistakes with high school math or simple counting when a question is phrased differently. So what's missing for true intelligence? Hassabis points to 3 key areas: First, true creativity. The ability to generate novel hypotheses, not just prove existing ones. He proposes an intriguing test. Give an AI a knowledge cutoff of 1901 and see if it can independently develop special relativity by 1905, just like Einstein did. Second, consistency. Current AI excels in specific domains but lacks the reliable, across-the-board competence that defines human intelligence. A truly general system shouldn't struggle with basic arithmetic while excelling at complex reasoning. And third, continual learning. The ability to acquire new knowledge and adjust behavior online from new experiences, rather than relying solely on initial training data. Based on these gaps, Hassabis predicts we are perhaps 5 to 10 years away from achieving AGI, and it will likely require 1 or 2 major scientific breakthroughs along the way. As AI's understanding of the physical world deepens, practical robotic assistants are becoming more realistic. DeepMind's robotics models can already translate natural language commands into precise physical movements. The question of form is particularly interesting. Hassabis now leans towards humanoid robots. As he explains, our world, stairs, doorways, furniture, is designed for humans. It's easier for a robot to adapt to our world than for us to redesign our entire world for them. DeepMind is pursuing a dual strategy, developing a cross-platform Android for robotics, while also creating deeply integrated solutions for specific robots. But he admits we are still in the early days. The algorithms and hardware need more development. He offers a vivid analogy. We might be in the 1970s PC era of robotics, with one key difference. A decade of progress now happens in a single year. Hassabis considers accelerating scientific discovery to be the core reason for his life's work. The breakthrough of AlphaFold was just the beginning. Building on its success, he founded Isomorphic Labs to revolutionize drug discovery. Their goal is to shrink the traditional drug development timeline, which can take years or even decades, down to weeks or even days within the next 10 years. Through partnerships with pharmaceutical giants like Eli Lilly and Novartis, they're focusing on cancer and immunology and expect to enter preclinical phases next year. DeepMind's AI systems are already being applied to material design, fusion reactor control, weather prediction, and solving math problems. However, Hassabis points out that AI's biggest limitation in science remains its inability to independently form new hypotheses or theories, a key challenge AGI must overcome. AI isn't just changing science, it's completely transforming creative work. Take Nano Banana, an image editing model integrated into the Gemini app. Tasks that once required complex Photoshop skills, like removing objects or adjusting lighting, can now be done simply by describing what you want. This change is happening on 2 levels. First, it's democratizing professional tools for everyone. And second, it's making top creators 10 or even 100 times more productive, allowing them to rapidly prototype ideas at very low cost. When asked about the world in 10 years, Hassabis predicts we will have achieved full AGI by then. This, he believes, will usher in a new golden era of science, a new renaissance, with benefits spreading across everything from energy to human health. Imagine a world where a single sentence can create a virtual universe, where robot assistants understand your every command, where treatments for diseases can be designed in days, and where the pace of scientific discovery is unprecedented. But perhaps most importantly, this future doesn't just belong to tech elites. Just as Hassabis journeyed from a bedroom programmer to a Nobel Laureate, the democratization of AI tools means everyone has the opportunity to become a creator, a discoverer, and a changemaker. Change in AI happens at lightning speed, but one thing is certain: we are standing at a historical turning point. And it all began with a young programmer's dream in the 1990s to teach machines to think for themselves. Thank you for listening. Don't forget to subscribe so you never miss our latest episodes. We'll see you next time.